This is Unit 1, Part 2, talking about water. And so we will continue our discussion on water and some of its properties. Another property of water is considered the universal solvent. What this means is that most substances will dissolve in water, and that gives us a couple of other terms that we need to know. For instance, what does the word solvent mean? Well, a solvent is a liquid that is doing the dissolving. So most of the time we think of this as water. For instance, the picture shows salt dissolving in the water. Well, the water would be the solvent. And so the reason water is able to do this, one of the reasons it's able to do this, is because of its polarity. See how it pulls the sodiums and the chlorines apart and causes them to dissolve in water. And in this case, the salt would be something called the solute. And so the solute is the substance that is being dissolved, and if you have a solvent and a solute that is equally distributed throughout the water, you have something called a solution. So again, in a solution, the solute is equally distributed. You can't tell where the solvent ends and the solute begins. You can't really see it floating around or anything like that. The other difference is with a suspension, you have this temporary suspension of materials. There's not any, or everything's not dissolving. Maybe some things are, but not everything's dissolving. Italian dressing is a great example of this because you have oil and vinegar and some like floaty stuff, and if you sit the Italian dressing on the counter or like on the shelf at Walmart, you kind of have, let's just pretend this is a jar of Italian dressing. Well, you're going to have like all the floaty stuff at the bottom, and then you're going to have a layer of like vinegar or oil, and then you're going to have another layer. And because it's a suspension, all of those things are not equally distributed, whereas if you set Kool-Aid on the counter, it is not going to like separate out. Italian dressing will. Great example of a suspension. A more permanent suspension, something that's going to stay suspended longer, is a colloid. Milk is a good example of this. Some of you have probably tested this in your rooms. If you poured a glass of milk and drank 2 drinks out of it and left it on your desk for several weeks, you'll notice that the fats have settled to the bottom to create some sort of nasty cheese, and then the liquid separated out to the top, and that was pretty gross. And so this is why you shake your milk, is to keep all of that circulated. You don't want to shake the milk that's still on your desk because that wouldn't help any. A couple other terms I just want to make sure that we're aware of before we move on. I believe I may have mentioned them, but are the terms hydrophilic and hydrophobic. The hydro, of course, means water. This philos or phileo, sometimes you'll see that as it's a Greek word for like or love, and so this is water loving. Usually hydrophilic substances are polar in nature because they like water is polar. Other polar substances and water get along. Hydrophobic, think of the word phobos. This is where we get our like phobia. These are water fearing substances. So like oil and water. Oil is non-polar. It does not like water. We will use these terms hydrophilic and hydrophobic quite a bit. A little bit more on the chemistry of water. Sometimes we will talk about moles of a substance in here. We're not going to be doing any calculations with that, but a moles of a substance just refers to the number of molecules of that particular substance in the solution. And it has to do with the concentration, if you want to think of it that way. So if you have a lot of sodium chloride in water versus a little bit, it's going to be a higher molar count. And so as far as our purposes, most of the time the molarity is going to be given, but we're not going to be needing to figure that at all. And so we won't be dealing with that sort of calculation, but I did want to make mention of it. One thing that we will look at is something called the dissociation of water. Think about the term association. If you associate with someone, you come together, you're with that person. And so to dissociate means to come apart. And we know that water molecules love one another. We talked about that. You see here, this is a hydrogen bond between those two water molecules. What happens with water in solution is this hydrogen here will be so attracted to this oxygen that it will actually pull that hydrogen off, as you can see, and make this thing called a hydronium, or an H3O, and leave something called a hydroxide. Well, as you can imagine, it's also going to pull that hydrogen back off. And so in water, where it's pure water, it's equally going both ways. This is not a thing. Normally we won't talk about hydroniums or anything. We'll just talk about hydrogen by itself, which is really just H2O, or that hydronium. I'm going to show you this real quick just so you're not confused. H3O is just H2O plus hydrogen ion. And so we're just going to leave out this part and just talk about the hydrogen ion and add to that this OH negative, which is called a hydroxide ion. And we're just going to look at it like this because I think that makes it a little simpler for our purposes. And so in pure water, you have this equal distribution of hydroxides and hydrogen ions. They're coming together as frequently as they're coming apart, and there's not a problem. Not that it would be a problem if there wasn't, but it wouldn't be pure water anymore. Anytime you have one that is more than the other, you have either an acid or a base. So if the hydroxide is higher than in solution than the hydrogen, this is called base. But if it's the other way around, and you have the hydrogen is greater in solution, you have an acid. Now, of course, this can be at varying degrees, right? You can have a ton more hydrogen than you have hydroxide, or just a little bit more hydrogen than you have hydroxide. And so that's why we have this scale to show us the relative amount of hydrogen to hydroxide. Normally, when we talk about this, we've always used the pH scale, which is just a measurement of the amount of hydrogen in the solution. And so the more acidic a solution is, the more, or the lower the pH will be. And so take this, for instance, hydrochloric acid. Very little hydroxide, lots and lots of hydrogen in the solution. The pH is going to be closer to 0. Whereas a really strong base, where there's very little hydrogen, lots of hydroxide, you're going to have a very strong base, like sodium hydroxide or ammonia, or bleach is going to be up here someplace. Okay? And so that's how we use the pH scale. The pOH scale, which you might see, we won't talk about it a whole lot here, but you may see it on the AP exam, is just the inverse of the pH scale. Notice, something that would be a 14 on the pH scale is a 0 on the pOH scale. And so my recommendation is to learn the pH scale. Base is high, acid is low, and then if you're ever asked to figure the pOH, just do the opposite of that. Now, in our bodies, there are lots of acids and bases that are being used. And of course, acids and bases both can be corrosive. And so the way that our body deals with that is something called a buffer. This is an example of that in the blood. Your blood maintains a pH of around 7.4. And so anytime the acid or base is increased, we'll use that anytime your blood becomes more acidic, for instance, which can happen. If you have too much CO2 in the blood, it can become a little more acidic. And so what happens is your blood, or the cells around your blood vessels, will release something called bicarbonate. And bicarbonate is a weak base to counteract the acid in the blood. This relationship that this bicarbonate does is it's called a buffer. It's a weak base that counteracts an acid, or on the other hand, it could be a weak acid that counteracts a base. Another example of this is in your small intestine. That food gets dumped right into the small intestine from the stomach where there's a really low pH. Your pancreas creates a substance just like bicarbonate that is dumped into that small intestine area and thus neutralizing the acid from the stomach, protecting your small intestines. If this doesn't work, then you can have like a heartburn, or the other way, it could be like acid reflux. And so this is why those things can occur. A couple more things about precipitation as it has to do with the environment. There's acid precipitation. Could be, we normally think of acid rain, but it could be anything really that has a lower pH than 5.6. 5.6 is the threshold for acid rain. Rain by itself is slightly acidic because of the CO2 in the atmosphere, but if there's too much CO2 in the atmosphere or too much sulfur or other compounds that create acid, that acidity can go way down. And so normally you see this with sulfur oxide, nitrous oxide, these things that are created by industry and the burning of fossil fuels. They can create sulfuric acid, nitric acid, two very strong acids that are not good for plants. They're not good for structures by us. Now you don't get the idea of like people running around with melting flesh or anything like that, but it does create some environmental issues. One of those issues that it creates is called leaching. Leaching is this idea of the rain pushing nutrients away from the roots. And when it does that, it causes the plants to just essentially die out. Um, the nutrients are pushed away from the roots, driven deeper or towards the surface of the ground and away from the roots, and causing those plants to die. And so this is not good. The lowest recorded acid rain, it was in Ohio in the 70s, is a 3.2, which is about like lemon juice or something like that falling down from the sky. So that's relatively acidic. Of course, there are human problems that can occur too. You know, here we see the degrading of this statue, but obviously less important than the destruction of the environment.